Assalamualaikum and selamat sejahtera to all of you. Alright, so today we'll start with module 7 Atmega 32 program control instruction. So what is program control instruction? So a program control instruction used to direct the flow of the program and allow the flow of the program to change, in which the way you want to control the flow of your program or your project, either it is one-way traffic, which is from top to bottom, or something like this, from top to bottom, or you want your project has many direction, either from top to bottom, right? And then it goes back to the top and then go back to the bottom, right? So you have two-way control of the project flow. One is the one-way traffic, the other one is many direction. Okay, the most basic kind of program control are skip and compare. Okay, this one is indication of a short change relative to the current program counter, and the second one here is a branch or jump, indication of change in program counter that is not directly related to the current program counter. Okay, let's look at the compare and skip instruction. Okay, there are few compare and skip instruction available in Atmega 32. One of them is SBRC. Alright, this one here stands for skip if bit in register is cleared. So SBRC instruction tests a single bit in a register and skip the next instruction if the bit is cleared. Right? So I take the pointer first. Right. So this is the syntax of the SBRC. SBRC RB, in which your RR is your destination register. Alright, so this is the operand, and B is the bit. Okay, the location of the bit that you want to see. If that bit is clear, then you skip the next instruction. If not, then you do the following instruction. Right? So let's see this example here. Okay, the first instruction here is SUB R0 RY, in which you want to subtract R1 from R0, and then SBRC R07. Alright, so now you want to see the value of R0 in bit 7. If that value is 0 or cleared, then what happens is you skip this instruction here. Okay, you skip SUB R0 R1, you do the NOP. If the SBRC R07 here, if the R0 bit 7 is 1, what happens is you do SUB R0 R1 followed by NOP. Next is SBRS. Alright, so SBRS stand for skip if bit in register is set. So please correct this one here. SBRS instruction tests a single bit in register and skip the next instruction if the bit is set. Right, so here is the syntax. SBRS RRB. Okay, your RR can be from R0 to R31, while B is your bit location from bit 0 to bit 7. If the bit that you want to check is 1, then what happens is you skip the next instruction. If not, then you do the following instruction. Right, so let's look at here. SUB R0 R1 and then SBRS R07. Okay, first you subtract R0 and R1 and then put the result to R0, and then this is your SBRS R07. So the result from R0, okay, you check bit number 7. If the bit 7 in R0 is 1, and then you skip this instruction here. You skip NEG R0. you do the NOP. If bit 7 in R0 is cleared or 0, what happens is you need to do the NEG R0 followed by NOP. Okay, let's look at this example here. Alright, first you subtract R0 R1 and then SBRS R0 R7. Well, let's say lah, your R0, after you do the subtraction, your R0 now has value 8, 7 for example. Right. So now what you're going to do is, alright, before you do this, execute this instruction here, alright, this instruction, what you're going to do is, first you need to convert this hexa value to binary number. Okay, because I think you not. Okay, I make it bigger, right? So this is 1000 for 8 while 0111 for 7. Okay, so this is bit 0, 1, 2, 3, 4, 5, 6, and 7. Now you want to check which bit? Bit number 7. So this is your bit number 7. Okay, since this bit here is set, which is have value 1 here at bit 7, what happens is, alright, you need to skip NEG R0 and do NOP instruction. Okay, let's say lah, if, right, if the result of subtraction, your R0 is 07 for, or 77 for example, alright, so you need to convert to binary. Okay, so this is your binary number. Alright, so SBRS R07. So again, you check bit number 7 in R0. Alright, so this is bit number 7 in R0. Okay, which is 0 or cleared. What happens is you need to do the NEG R0. You cannot skip the next instruction here, the NEG R0. You need to do the NEG R0 followed by NOP. Right, so there is SBRS and SBRC. Same apply with SBRC, in which you check the bit location, see whether it's clear or not. If clear, skip the next instruction. If not, you need to do the next instruction. Right, next we have the CP. Okay, CP stands for compare. This instruction performs a compare between two registers RD and RR, and none of the registers are changed. The value of the register remains, no change. Right? Right, so this is the syntax CP RD RR, in which your RD and R can be from R0 to R31. Okay, this is the operation RD minus RR. Okay, you only want to check, you do the comparison, in which the CP instruction used to check this flags here. Okay, this flag will change accordingly to your operation here, this operation here. Okay, so for example here, CP R4 R90, you want to compare between value in R4 and R90. Alright, and then you have the instruction branch not equal. Okay, so branch not equal means that if the R4 value are not equal to R19, what happens is it will go to this not EQ here. It will jump to here. Okay, this instruction. If R4 equal to R19, what happens is you need to do the following instruction down here. You cannot jump to not EQ because R4 and R19 is equal. Okay, next we have the CPC. Alright, so CPC stand for compare with carry. So the instruction perform or compare between two registers RD and RR, and also takes into account the previous carry. Alright, again, none of the register value are changed. Alright, the value are still remain the same. All condition branch can be used after this instruction. Alright, so this is CPC RD. This is the syntax here, and then this is the operation RD minus RR minus with C, and none of the RD and RR value are changed. Right? Only after you execute this instruction CPC, what happen is your flags, alright, in your status register will be updated or will change accordingly. Right? So let's look at this example here. Alright, so now this one here, you want to compare between two 16-bit number. Alright, so what you're going to do is, okay, first, okay, since this is 16-bit number, so since 16-bit number, right, for the 16-bit number, for example, we put here, okay, for example, 1729, for example. Alright, since this is a 16-bit number, so you can divide it into two parts. One is low byte and the other one is high byte. Alright, and then this is the another 16-bit number, right? For example, alright, so one is low, the other one is high byte. Okay, for the low byte, okay, what you're going to do is we use the CP instruction, okay, to compare the low byte, while for the high byte we use the CPC instruction, similar to what we done in the arithmetic operation, right? So here you want to compare these two 16-bit number here. If these two 16-bit number here are not equal, okay, in this case 1729 are not equal with 1730 here, so what happen, this one here will be go or will jump to this and not EQ instruction, which is NOP. Alright, this is the branch destination. Alright, because these two number are not equal. If these two number are equal, let's say the top one is 1729, the bottom one here also 1729. What happen is you need to do the following instruction after the BRNE instruction. You cannot jump to this level not equal. Okay, right, next we have the CPI. Okay, so this one here you want to compare with an immediate value, right? So this perform a compare between register RD and a constant. None of the register are changed. All condition branch can be used after this instruction. Right? So this is syntax CPI RDK. Since again, I always highlighted, okay, every time your instruction here ended with I, what happen is you only can use the general purpose register from R16 to R31 only. Okay, K is a constant number from 0 to 255 in decimal, or 0 to FF in hexadecimal. So this is the operation RD minus SKEE. Okay, since this is a compare, your RD will not change, but your status register will be updated accordingly. Alright, for example here, you want to do CPI R19 3. Alright, you want to compare the value of R19. Is it equal to 3? Is it equal to 3? Okay, again here we use the BRNE. BRNE stands for branch if not equal. If the R19, the value inside of R19 is not equal to 3, what happens is you jump to this not equal instruction, which is NOP. Alright, this is the branch destination. If let's say the R90, the value is also 3, then value is same, equal, what happens is you need to do the following instruction after BRNE instruction. Alright, and then next is CPSE. CPSE stand for compare, skip if equal. Alright, so CPSE instruction perform a compare between two register RD and R and skip the next instruction if RD equal to RR. Okay, it will. Okay, so the next instruction will be skip. Alright, if the RD equal to RR. So this is the syntax CPSE RD RR. Operand R you can use from R0 to R31. Right, so let's see the examples here. Increment R4. Okay, so you increment R4 and then you do the CPSE R4 with R0. You want to compare R4 with R0. If R4 and R0 is equal, okay, the value is same, what happens is you skip this instruction here. Right, so you need to skip this instruction because R4 and R0 is equal. Okay, and you need to do the NOP. The next following instruction is NOP. If R4 and R0 are not equal, what happens is you need to do the NEG instruction followed by NOP. Alright, so that is for the CPSE instruction. Okay, now we continue with jump or branch instructions. Okay, there are two types of jumping or branching that are available in Omega 32. The first one is unconditional branch, in which when CPU execute an unconditional jump, it jump unconditionally. Means that you no need to see the condition either it is met or not. Okay, you force the CPU to jump without any condition to the target location. Example of unconditional branch are such as RJump, JMP, IJump, and etc. Okay, next we have the conditional branch. The second one is conditional branch. This one here, when CPU execute a condition jump, it checks a condition. Means that before the CPU jump to the target location, the CPU needs to check the condition first. Okay, the condition can, if the condition is met, then after that the CPU will jump to the target location. So this condition are inside of your status register, in which you can see the carry flag, zero flag, overflow flag, sign condition, and any other flag that are there you need to check before you make the jump to that target location. Okay, if the condition is false or the condition is not met, then what happens is the CPU will execute the next instruction after this conditional branch. Okay, first let's look at the unconditional branch. We have a three unconditional jump or branch in AVR. One of those is JMP, and then we have RJMP and IJMP, right? So the location where we want to jump is labeled by using any label or any name that you want to use, okay, followed by a colon here, right? So in front of the jump instruction, we mention the name of the label. Okay, so this will cause the CPU to jump to the location we have labeled instead of executing the instruction. For example, here you see here, this is the label that I mentioned previously. So this is the label 1 and this is your label. Means that you want to jump to this label here. Alright, any name, you can put any name here. You can put your name, your friend's name, or any others name that are necessary. Right, the first instruction that we want to, okay, that are available in unconditional branch is JMP. Alright, JMP stands for jump. This instruction jump to an address within the entire program memory. Alright, it depends on your program memory lah, your flash memory. Okay, for Omega 32 we have 32 kilobyte program memory, so it can jump from address 0 to the end address of our program memory. Alright, so this is the syntax JMPK, in which K is your memory address of your program memory, depend on your program memory sizes, right? So what happen is this K here will put to your program counter, and then the program counter know that you want to go to that location. Okay, so in the JMP, the operand contains the address of the destination. When a JMP is executed, PC or program counter is loaded with the operand value or with the address value. Right, for example here, this is the program here. You see here, this is your program memory address, starting from address 000. Why 00? Because we origin our program address at 0. Right, so this is our program memory, and this is our instruction or program. Right, the first one, LDI R6015. So what happens is you want to put 50 to R16, and then LDI R75. Okay, you see here, this is your program memory, program counter. The program counter will increase by 1. All right, and then now what happens is you execute the previous instruction. Okay, you can refer to your module 2 or module 3 if not mistaken, okay, to see what is the fetch and execute cycle is all about. Right, next, program counter 2 means that now the program counter point to this address, and then currently we execute this instruction here, LDIR75, means we put 5 to your R17, and you see here the next instruction that the processor want to execute is JMP label name. Okay, you see the label name is here. This is your label name. Alright, this label name is located at what address? 006. Alright, so this 006 will be placed to your program counter here. You see 006 go to your program counter. Now the Microprocessor or your processor know that now you are going to jump from here, address location 002, to program address location of 006. Right, so you execute this line here, and then suddenly at this line here, okay, you have another JMP instruction which is with a label name. What is the label name here? What is the location of this label name? Is the location of our label name is address 006. So this 006, you will it will put inside of your program counter, your PC, and then the PC go to address 006, and it will keep repeating. Okay, depends on your programming. Right, next we have the RJMP. RJMP stand for relative jump. Right, so the instruction is to jump to an address within this size here. Right, so for every ARM with program memory SCD 4K words, this instruction can address the entire memory for every address location. The difference between RJump and JMP is the way the processor take the address are different, but it will jump to that address. Okay, so this is an example. Okay, we skip this one. We go to another slide to see it more clearly. Right, so this is the same. Okay, this is the program which is quite similar to the one we have earlier in the JMP section, but instead of using the JMP instruction, we use the RJMP. Right, so since this one here, you see this program is started at origin 0, so that's why your program memory started at 0 and etc. Right, so we do this one. This one is your program counter. This is your program counter. Right, so here you are currently what we call here, you currently execute this instruction here. All right, then the program counter is increased by 1, and now RJump label Alright, so now the next instruction that the program counter need to execute is rjump label name, in which your label name here is located at this address 0005. So what happened here? So what happened? Instead of taking the 0005, right? Supposed to 005, you see here, this is supposed to 005. Okay, what happened is previously we take the program counter directly to 005, but now for the rjump, all right, started from here, all right, which is 002, to go to 005, you need to add 1 2 3 addresses. All right, so that's why here you see 003 plus with 002, and it contribute 005, and then after that the program counter go to this instruction or to this program address. Okay, the way the microP get the address are different from using the JMP and RJMP, but it produce the same branches or jump, okay, direct to that location. Alright, so you see here, when rjump is executed, the operand will be added to the current value of PC plus 1, and then another plus with addresses that you want to go. Okay, the different addresses that you want to go. Okay, so we see here, it is currently 006, and then you're going to go to 005, so you need to add 006 to, and it becomes 007, and plus with FFE, and it will produce a 005. So now the program counter go back to address 005. Okay, that is for the RJMP. What about IJMP? IJMP stands for indirect jump. So this INJP instruction indirect jump to the address pointed by pointer registered Z. So you need to look at what is the pointer registered Z pointed to, then it jump to that address. Right, so while it is useful to be able to jump around in your code using JMP, IJMP, RJump, they certainly don't solve all the problems. Okay, so in order to write a real program, you need to be able to branch conditionally based on the current state of the program. So that's why another way to do a jumping or to do a branching, we use the conditional branch. We do not force the microP to jump without certain conditions are met. The conditions are stored in the status register. All right, you have 8-bit status register. You have 8 type of flags, starting with I flag, T flag, H flag, S, V, and Z, and C flags. Okay, so condition branch instruction examine the bit in status register and choose between two course of action. Okay, the status register bit are either updated after a certain instruction have been executed or explicitly updated by using the test and compare instruction. Okay, so this is the status register review. You have 8 type of flags here, starting from I, T, H, S, V, and Z, and C, and then you need to make sure that the condition, the certain flag is true or it is met before you do the jumping branch. So the conditional branch instruction is identified by the minimum unit BRCC. Okay, every time you see the BR, you know that that is a conditional branch instruction where CC represent the condition to be checked. Okay, so this is the general form. BRCC, your address label. All right, you can. This is BR stand for branch conditional, and followed by your address label where you want to jump or where you want to branch. If the condition is true, then control will branch to that address label, so no effect on that condition goes. Okay, there are several types of condition branch instructions. Started with here BREQ. All right, BREQ stand for branch if equal. All right, so this branch here only taken if your Z flag equal to 1. Okay, what means the Z flag equal to 1? Means that if you have two same number. Okay, for example, you have 5 minus with 5, the result is 0. Okay, when the result is 0, the Z flag will set 1. Okay, you know that one is those two numbers are similar. Okay, for the BRNE, so BRNE stand for branch if not equal. Okay, so this branch is taken if the Z equal to 0. Okay, for example, earlier we have first number is 5, the second number is 5, you 5 minus 5, you get 0, and then what happens is your Z equal to 1. Is by using the BRNE is can you do a jumping or branching? No, cannot, because the Z not equal to 0. Right, and then there are few condition branch instruction that you can see here, right? So in this courses here, we only take a look at the few from here, and then to see the detail. Okay, the next one is BRGE. BRGE stands for branch if greater or equal. Okay, this is for the sign number. So BRGE instruction test the sign flag. Okay, you see that it needs to set the sign flag and branches relatively to the PC if S is clear. If the S is equal to 0, then it branch. If S, your status, your S flag equal to 1, what happens is the branch not taken. Okay, so this is syntax BRGEK. So this is the operands. All right, and then this is where it want to branches. Okay, for example here, first you need to compare R11 and R12. Okay, you compare between two registers. Okay, the first register have a certain value, the second register have a certain numbers. Okay, so if R11, okay, after you compare, and then what happens is if R11 greater than R12, okay, then what happens is the branch will taken to this GRETEQ instruction. Okay, it will go to this instruction here. If R12 is greater than R11, what happens is you need to do the following instruction after the BRGE instruction. Okay, next we have the BRLT. Okay, so BRLT stands for branch if less than 10. Okay, this is for the sign number as well. Okay, so BRLT instruction test the sign flags and branches relative to the PC if the S is set. Okay, when S is set, means that you have the sign number. Okay, it means that that number is smaller than the number that you want to compare. Alright, so this is a syntax. Okay, we see the example here. CP R11 R12 BRLT less. If R11 smaller than R12 means that you have a sign number. Okay, 5 minus with 6, so you get negative 5. Okay, so negative 5, the sign number will become 9. So what happened here? You know that the R11 is less than R12, so it will branches to this operation here. If R11 greater than R12, what happen here? S will get 0. Okay, for example, 7 minus with 5, you get 2. 2 is positive number, so S will the sign flag will get 0. And what happen here? After you do this condition here, what happen? Right, okay, so that you need to do the following instruction. You cannot branch to this LES and OP. Okay, then we have the BREQ. Alright, branch if equal. Okay, so this one here test the 0 flag and branches relatively to the PC of the program counter if the Z is set. Okay, for example here, compare R11 with R12. If R11 equal to R12 means that both numbers are same, and when both numbers are same, what happens is Z equal to 1. Okay, you have the first number is 5, the second number also 5. You compare 5 minus with 5, you get 0, so Z equal to 1. What happens is you know that both numbers are equal, and then it will be branched to this instruction here. And what happens if not equal? You need to do the following instruction after BREQ. Okay, then we have a BRGE. Right, so this instruction test the zero flag and branches relatively to the PC if that is cleared. Right, so CP R11 R12. Okay, you compare these two numbers here, register 11 and register, and if register 11 not equal to register 12, okay, R11 for example 5, R12 is 7, what happens is both numbers are not equal, Z equal to 1, sorry, Z equal to 0, and then what happens is, okay, you know that both numbers are not equal and it will branch to here. If not, if both number is equal, what happens, you need to do the following instruction. Okay, let's look at some exercises here. Okay, determine if the highlighted branch will be taken or not. Okay, so the first instruction here. LDI R16OX70, LDI R70OX11, SBRC. So what is the SBRC do? The SBRC means that you want to skip bit if register is clear. Right? So first, what you're going to do is, okay, so R16. R16. Okay, so this is R16. R16 equal to 7E. 7E. Okay, so what you're going to do here is you need to convert this 7E to binary number. Why? Because we want to check bit 3 is it cleared or not. Alright, because SBRC R16. Okay, you need to check the R16. Okay, so 7E. Where is 7E? 0, 1, 1, 1. What about E? E is 1. E is 14. 1, 1, 1, 0. Right, so bit number 3. Where is bit number 3? This is bit 0, 1, 2, and 3. So this is bit number 3. Okay, so what happened here? This bit number 3 here is 1, is set. So what happened? Is it skip the next instruction dia BRPL or not? No, in this case here, okay, you need to do the BRPL semula. So in this case, if the highlighted branch is taken or not, the answer is not taken. Okay, so this is not taken. Okay, why? Because this branch here, this instruction here are not skipped. Okay, why? Because bit number 3 is 1, not 0. Okay, the second one here. Okay, load I R60 OX70 out DRA R16 SBIC DDRA5. Okay, what happened here? Right, so first what happened? R16, what is the R16 value? This is R16 value, and this value here you send out to your DDRA, so automatically your DDRA will get the same value of R16, which is 7E. Okay, so now what you're going to do is, okay, SBIC DDRA5. Okay, skip bit if IO register are clear. In which bit? Bit number 5. Okay, so this is 0, 1, 2, 3, 4, and 5. So this is bit number 5. Okay. Okay. Is it bit number 5 is cleared or 1? It's 1. It's set. So what happens if set? Means that the branch not taken as well. Okay, it means that you need to do the JMP semula, no operation, so not taken. Okay, the third one here. Okay, LDI R16 OX7E, LDI R70 OX11 at R16 and R70, and then BRNE semula. Okay, what happened here? Okay, so R16, what is the value R16? This is the value of R16. And then R70, what is the value of R70? One. Okay, so what is 1 in binary? 0 0 0 1 followed by 0 0 0 1. Okay, you want to add this both number here, so add add, so add R60 R70. So R60 we have new value. What is the value here? Okay, we see later what are the value. Okay, you do the addition operation. Alright, so this is right, 0 plus 1 you get 1, 0 plus 1 you get 1. Okay, and then this one also 1, 1. Okay, so this one is 1 1 1 1. Okay, followed by this is 0. Okay, you have carry, so this is 0 as well. Right, so this is also 0, and this is 1. Okay, so this is the value after you do the what we call delete. Yes, correct. Right, after you do that, so you get is 8F, 8F. Alright, so now BRNE similar. Okay, what is BRNE? After you do this addition, alright, so BRNE, what is the BRNE do? Okay, so we see that what the BRNE. Okay, BRNE branch if not equal means that we need to see the Z. If Z is clear, then we branch. If Z is 1, then it's not branch. So based on this what we call exercise here, okay, after you do the addition, what happened to your Z flag? Your Z flag equal to 0. Why 0? Because you have value here. So what happened? So in this case here, the branch will taken. Okay, why? Because Z equal to 0, so it know that this number here are not equal, and then it go to the similar. Okay, location, similar location.